One of the most common op-amp circuits is the inverting configuration. In this configuration, an input signal, which we'll represent as a sinusoidal source, although it can be any signal we want, so we'll call that V sub I, is fed through a resistor, R1, into the inverting terminal of our op-amp. The non-inverting terminal is connected down to ground. The inverting terminal also has another resistor, R2, connected to it, and R2 feeds to the output, Vout. The output voltage, Vout, will be measured between the output terminal and ground. Now we'd like to find the gain of our circuit. The gain of the circuit is simply a relationship between two different voltages. Usually we're interested in the output and how it responds to changes in the input. You'll recall from superposition that all node voltages in a circuit are linearly related to the independent sources. We have one independent source and we're interested in one output voltage. So the gain for our purposes is simply finding the ratio between Vout and Vin. To perform this analysis, probably the best thing to do is to replace the op-amp with the model that we developed in the previous lecture to simplify our analysis. Remember, the op-amp's model had two input terminals, and the difference between them, Vx, we'll label that Vx, plus and minus in that orientation, controls a dependent source which has an infinite gain, but we're going to let the gain equal A at this point, and then we'll substitute A is infinite later when we get to it. One side of that source, as you'll recall, was grounded, and the other side led to the output of the op-amp, plus and minus, where the output was measured between the output terminal and ground. On the other side of the op-amp, the non-inverting terminal is connected directly down to ground, while the inverting terminal has a resistor R2 connected to it, and that is connected to the output node, so we can draw R2 in there, and it also has R1 connected in here that connects back to our input source, and the input source goes down to ground, and so that completes our circuit. Before proceeding, you'll note that the little ground symbols mean that this node, this node, this node, and this node are all connected in a common node. Now, to analyze the circuit, we can approach it any way we want. Given our knowledge to this point, it probably makes sense to proceed with nodal analysis. So the first thing to do is to identify the nodes. We have our common reference node right along here, which I'll just highlight so we know where it is. That's our reference node. We'll have another node V1 at this terminal here. We'll have node V2, and lastly node V3. But if you're observant, you'll realize that we have a supernode at V1, which connects V1 to ground through an independent source V sub I. So we can write right away that V1 is equal to V sub I. The second supernode we notice is at the output, where we can see that V3 is actually our output voltage directly. The other thing we can see is the output voltage VO will simply be equal to A times Vx, where Vx is this voltage here. But you can see that Vx is going to be the negative of V2, so we can write that Vx is equal to minus V2, or we can substitute in and say that the output voltage will be equal to minus A times V2. It will be handy for us later to take the reverse of this and say that V2 is actually going to be equal to minus the output voltage divided by A. Now I want to point out a very curious thing here. A goes to infinity. If A becomes infinite, provided our output voltage VO is a finite value, then V2 will become 0. That means that the positive and negative terminals of our op-amp are going to have the same potential, but no current flows through them. We call that a virtual short. Now we're ready to begin our nodal analysis with Kirchhoff's current law at V2 or KCL. To begin nodal analysis and Kirchhoff's current law, we should identify the currents. At this node, we're going to have a current I1 flowing back towards the source, I2 flowing into the amplifier, but we do know one thing about the op-amp, and that is the currents into the op-amp must be zero, so I2 will be zero. Lastly, we have a third current, I3, flowing through R2, or I1 plus I2 plus I3 must be equal to 0. We can now replace I1 with V2 minus our input voltage VI divided by R1 plus I2, which we know is 0, plus I3, which is the current that flows from V2 to our output, minus Vout divided by R2 equals 0. We can multiply this equation through by R2 and by R1 to clear the fractions, so we'll get R2 times V2 minus R2 times our input voltage VI plus R1 times V2 minus R1 times Vout. Will all add up to 0. We can group together the V2s and rearrange, so we can write now that we'll have minus R2 times VI plus R1 plus R2 times V2 minus R1 times Vout equals 0. Well, this equation relates our input voltage, VI, to our output voltage, but it has a V2 in here that we don't really want. If we look back to the marginal thinking we had over here, we can see that V2 is going to be equal to the negative of our output voltage divided by A, so we can make that substitution and continue on. So we can write now that we have minus R2 times our input voltage, plus we'll have R1 plus R2 times minus the output voltage divided by A minus R1 times the output voltage will be equal to 0. We can clean the equation up by moving our Vouts to one side and our Vins to the other side. If I do that, I'll get R1 plus R1 plus R2 over A, all times our output voltage, will be equal to the negative of R2 times our input voltage. Maybe I look a bit more like a 2. That will be helpful. Now we can rearrange our equation to solve for the gain that we're interested in, or we can write that Vout over VI will be equal to minus R2 over R1 plus R2 over A, and that becomes our gain. Normally we don't see it in this form. Usually it is rearranged by dividing the top numerator and denominator by R1 to get R2 divided by R1 divided by, need a little bit more space here, divided by 1 plus R2 over R1, all divided by A. This is the inverting gain of the amplifier, but as A goes to infinity, if A goes to infinity, then this term here will go to 0, and we're left with the output voltage divided by the input voltage is simply given by the negative of R2 divided by R1. And this is the gain of the inverting configuration. From this analysis we can observe 3 things. The first one we note is, remember, no current flows into the op-amp, and this was useful for us. The second thing we noted was the existence of the virtual short between VI and plus and VI minus, or VI plus will be equal to VI minus, but no current flows between these two. The last one, the third item, which is perhaps the most curious, is that the gain only depends on the resistor ratios. Note that even though we need the op-amp to make the gain happen, only the resistors determine the actual value of the gain, which certainly makes things very simple for circuit designers. You just pick the resistor values you need to get the gain you want and use an op-amp. You might say, well, what was the op-amp for? Well, the op-amp was essential to make the whole thing happen.